Hello?
Hello.
Okay, so saying hi to all our sunburned friends. Sunburned. Because the people that are watching this are actually not in class. You're here now. We're talking about the person that's in Hawaii. Anyway. No. Okay, uninhibited and inhibited growth and decay. So now, think about it like this. So growth, what does that do? Okay, so the population would do what? Increase. Decay, population will?
Decrease.
Thank you. All right, so inhibited. Okay. Inhibited, what does inhibited mean?
Stopping it somehow?
Somehow stopping it, very good, yeah. So there's something that's going to restrict it. And what about uninhibited?
It's nothing stopping it.
No restrictions on that. Right? There's no restrictions. All right, solve differential equations involving uninhibited growth and decay. It comes out something like this. Okay. There are situations in science, nature, and economics, such as radioactive decay, population growth, interest paid on investment, in which a quantity A varies with time t in such a way that the rate of change A respect to t is proportional to A itself. These situations can be modeled as a differential equation. D of A over D of t is equal to K of A, where K is not equal to 0 is a real number. It'll make sense here in a minute. All right. So if K is greater than 0, it is going to be a growth model. If K is less than 0, it's going to be a decay model. Suppose the initial amount, A sub naught, now A sub O, sub 0, it's could be said I haven't talked this much over the last week. Did my best to avoid everyone. I know there's cough drops here. Ah, yes. Ricola. All right. Okay. Suppose the initial amount, A sub naught, this is A sub naught initial amount. Okay? Initial amount of the substance known, given us the boundary condition, initial A is equal to A of 0, or A sub naught when t is 0. Initial amount, starting amount, when time is 0. That's really important to understand. So if it's your initial amount, that means time is 0. So no time is elapsed, you have your starting amount. Okay? We solve differential equations in the form of dA over dt is equal to K of A by writing dA as, okay, so now there's some algebra that goes into this. So we have dA dt equals Ka, multiply both sides by dt, and then divide by A. Okay, so right here, so it's going to multiply by dt and then divide by A. So I should end up getting dA over A equals K dt. And we integrate both sides of the equation on the left respect to A and on the right respect to t. So all your A's are on the left, and on the right you have respect to t. So I'm doing the integration in terms of t on the right, integration in terms of A on the left. So the whole thing, all the way down, blah, 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 all the way to here. A is equal to A sub naught times E to the KT. I made sure I put all the algebra in there for you, where a sub naught is the initial amount. So we're trying to figure out the initial amount. So when I get the initial amount, I'm trying to figure out the time, all that. I get the time, the whatever rate it's changing, it's either growth or decay, and I'm going to have a certain amount at the end. That's what the A by itself means. I'm looking for a certain amount. All right. So rates in which that exponential law of uninhibited growth or decay, or in business context, the law of continuously compounded interest. Okay, so this right here where k is greater than 0. So now let's think about that slope. So what do we know about the slope?
It's increasing.
It's increasing. At what rate though? It's increasing at what rate? So here, let me put it like this. So I have a tangent line right there. Tangent line right there. Tangent line right there. It is increasing, right? At what rate? So let's say this slope right here, the first one is 1/2. This one is 1. This one's 2. That's increasing, isn't it? At what rate? At an increasing rate. That's what we need. So it's increasing at an increasing rate. So it's going up, but it's going faster as it goes up. So that's increasing at an increasing rate. So, okay, same information. This right here is going to be decreasing at a decreasing rate. So it's starting to decrease, so it's decreasing fast here, not so fast here, and slow here, right? Is that okay? Okay. All right, assume that a colony of bacteria grows at a rate proportional to the number of bacteria present. If the number of bacteria doubles in 5 hours, doubles in 5 hours, how long will it take for the number of bacteria to triple? Okay, so what is my formula? A equals A sub naught e to the kt, right? All right, couple things I know. I'm going to have some value. So the number doubles when? In 5 hours. So I know that I'm going to end up with what in 5 hours? So it's going to be 2. Okay, so it's going to be 2 A sub naught when okay, how long would it take for a number to triple? Grows at a rate proportional to the number of bacteria. Okay, so couple things I know that at I have A sub naught when t equals 0, right? Okay, can I plug that in? Yeah, let's plug it in. Let's see what we get. So right here, when I plug this in, so that's going to go in there, and k times 0. What is 0 times k? 0. And e to the 0. Anything times 0. Anything times 0 is 1, right? Okay, so I know that when a of 0, right, is equal to I have A sub naught e to the k times 0. So all this right here is going to be A of 0 equals A sub naught. Oh, yeah. Basic, right? It makes it a little bit easier if I had numbers in here, but it's really not that important because I'm trying to find out the rate for this. So in this, I actually have 3 variables. I have the A sub naught, I have the K, and I have the T. All right, so now I know that I could say that A sub naught is just going to be A sub naught, whatever my initial is. Okay, and I know that when I have this, okay, so let's plug in that to see what we get. So I know I'm going to have 2A sub naught equals A sub naught e to the 5k, right? Yeah, let's do some algebra, right? Divide both sides by A sub naught, which is whatever my initial amount is, right? So I should get 2 is equal to e to the 5k. And how do I undo an e? I ln, right? So it's going to be ln 2 equals 5k, right? And then divide both sides by 5. Okay. So I now have a equation for this. So my new equation is going to be A is equal to A sub naught e to the t times ln 2 over 5. All right, so the reason why I left it like that is I don't want to put it in the calculator yet. I don't. It's going to make life a little bit hectic having that nasty decimal. Did I lose anyone? Are we okay? Yes, good? Okay. So from here, so now I have my rate, I have my time, and I have my amount. I'm just going to say it's A sub naught, right? How long will it take for the number of bacteria to triple? Okay. So now I'm going to be looking for 3 A sub naught, right? So I'm basically looking for 3 A sub naught. So let's plug that in. So 3 A sub naught is equal to A sub naught e to the t times my ln of 2 over 5. And I'm trying to solve for the t value, right? Because it's asking for when is t, at what time will this triple? Okay, so let's divide by A sub naught. So 3 is equal to e to the t ln 2 over 5. ln 3 equals t times ln of 2 over 5.
So you just ln both sides to get.
Yes, I ln both sides again, because if you notice the e's now gone. So if I ln both sides, I can get rid of the e. All right, so it's going to turn into what? So since I'm going to divide by that, and so it's going to be 5 ln 3 over ln 2 is equal to t. Yeah, I could plug it in there, right? Or I could do a little bit more.
We just needed
Yeah, we just need the time. Now I got the time. Let's figure out what that time is. 5 ln 3 over ln 2. No, it's not like I don't trust you, but we also have some people that are burnt sitting in Hawaii. And 7.92. Okay, remember this is AP calculus, right? How many decimals? 3. So it's going to be 7.92. There we go. So T. All right, so now what is the rate? What is my units on that? Hours. Okay, does that seem right? It takes 5 hours to double, and basically 8 hours to triple. So it's increasing faster, isn't it? Yeah. Okay. Good. Radioactive substance. The rate of decay is proportional to the amount of substance present at a given time. Radioactive. So where K is less than 0 depends on the radioactive substance. Half-life. Subject time required for half of the subject to decay. So the half-life, that's an important thing. So half-life, half-life, half-life. How much is it? Half, right? No. You guys, you think I'm joking.
Okay.
This is a major concept to understand, especially when we're doing these math problems. And you're looking at it, you're like, I don't know what to do. Okay, I'm looking for how much? Half. I'm looking for half, right?
Yes.
Okay, there we go. All right, so it's going to decay. Skull of an animal found at archaeological dig contains 20% of the original amount of carbon-14. If the half-life of carbon-14 is... How long ago did the animal die? What?
Half-life.
Wait, how long did the animal die ago? Like, how long
Is the
time
half-life-
ago? Or
Half-life.
how long it was dying?
How long ago did the animal
Okay,
die?
okay.
Look, it said ago.
Yeah.
Skull of an animal died.
Remember, English is not really his first language, so...
Okay, read the question again.
Okay.
Let's understand.
The skull of an animal found archaeological dig contains about 20% of the original amount of carbon-14.
Okay.
Okay. If the half-life of carbon-14 is that many years, how long ago did the animal die? Okay. So, think about it.
Half-life.
Wouldn't it be like
Half-life.
2.5 of those?
Okay, so, think about it.
Yeah.
I have how much left?
20%.
20%. Okay. So, I know at some time t, right? At some time t, I'm going to have 20%, which should be 0.2, right? 0.2 is going to be left. 0.2 times whatever my amount is, right? So watch, I'm gonna make this a little bit easier. So 0.2 times a sub 9. Okay? And I know that there is half. So in time 5730, I have half. So I should have 0.5 of my a sub 9. Okay, so now I have two values. I have two values that I could actually go with.
Why the 2?
Why 0.2?
Yeah.
20%. Yeah, 20%, 0.2. Okay, so now I have two places. So I need to use this one to give me K. Does that make sense? I have a point that is going to be my T value. That is going to give me my and my A sub naught, right? It really doesn't matter. So if it's going to say, so many micrograms, or they're a ridiculous amount, milligrams. I don't even think it's milligrams. It's really, really small amounts of the rads of this. So anyway, all right.
Wait, where'd you get the 0.5?
Okay, so wait, hold on. Right here. Stand right here. Okay, you ready? We're looking for the
Oh, okay.
Half-life.
half-life. Okay, there you go. All right.
It was just a test.
I know.
Yeah, to remember.
The big picture. That's the reason why I keep emphasizing it. Is half-life. So let's go ahead and plug this in. So I know that I'm going to get 0.5 of A sub naught is going to be equal to A sub naught e to the 5.730 times K. All right, is this getting pretty easy now?
Yes.
It's just some algebra, and it's just a new concept.
It's a lot of algebra.
Okay, so now what's going to happen to my A sub naughts?
Go.
Go away!
Why?
Because I'm dividing both sides by A sub naught.
But then they're
Go away.
But they're your friends.
Huh?
We
You're
can bring it
killing
back
your
later.
close friends, Pacho.
All right, so 0.5 equals e to the what? 5730K. You know what? We could do a little bit of algebra and turn that into 1/2. So when I do my ln, it's slightly different, but you're gonna get the same answer anyway. All right, so watch this. So isn't 0.5 1/2?
Yes.
Yeah.
Okay, so I'm gonna do 1/2. So let's call this 1/2 equals e to the 5730K. ln both sides, so it's gonna be ln of 1, right?
Why?
Because this is a fraction, isn't it?
Yeah.
And with my ln, my log rules, it's gonna be the top minus the bottom, isn't it? So it's gonna be ln 1 minus ln of 2. You'll see why. You'll see why here in a second, okay?
No, I just don't know what rules. That's it.
Oh, you don't know the log rules?
No.
Okay. So if it's division,
Okay.
it becomes a minus.
Okay.
If it's a multiplication, it's a
Oh,
yeah.
okay.
So if it was
That's
like
pretty easy.
2 over 3, it'd be ln2 minus ln3.
Yeah.
Okay.
Yeah, that's basically what we're doing. So
Okay.
and it helps out later on when you're combining too. So anyway,
Sure.
equals 5730K. Now, you got your handy dandy calculator right now.
I do.
So what is ln1? Try again.
Oh wait,
0.
0. Thank you. ln1 is 0. So what that's the reason why I set this up like this with my fraction. So my ln1 is going to give me 0, right?
Yeah.
So I could just clear that off. That's the reason why I did that. And then divide by 5, 3, 5,
5730.
It's 0.0001.
Wait, what?
5.
730
Negative 0.0001.
equals K.
Equals K, right?
Okay.
Alright.
So now I have a value for K.
Yeah.
And keep that value right now. Okay, we're not gonna decimal it yet, because I'm gonna need to find the year for this. And if you approximate the answer at one point, especially when we're dealing with thousands of years, it's gonna be off by factors, by however much that you rounded by. So there's my K. Insert page right here. So I have my K. So now we're trying to look for 20%, right? So now it's going to be 0.2 A sub naught is equal to A sub naught equals, crap. Can someone go turn the fan on, please? E,
I need to know.
T, just hit the circuit breaker on the side.
What is that?
The power strip, sorry.
What is that?
No, because that's about ready to kick on, so you could actually hear that screaming at me. Negative ln of 2 over 5730. Right? So we're using our second point now, because we had 2 points to start off with, right? That's the reason why I always try and do this. I set it up with 2 points, so now from here, let's go ahead and do our math. My asymptotes go away, so I'm now going to be left with 0.2 equals E t negative ln of 2 over 5730. I'm going to turn that 2 into a... Do I want it as a fraction? No, I don't. That's going to be 0.2. It's 1 over 10, isn't it? 1 over 5, right?
Yeah.
Okay, yeah, sorry, 1 over 5. So it'd be ln of 1 minus ln of 5 equals, right? That's going to be negative ln of 2 over 5730 times t. Right? The ln1 goes away. 2 negatives make a... There we go, it's a positive. So it's going to be basically 5730 ln of 5 over ln of 2. $13,304.04. Point what?
6%.
And what does that actually represent?
How many years?
Years, okay?
Years ago, isn't it?
Years old.
This is how long ago did it die?
Mm-hmm. So that's how old the skull is. So at the moment of death, your body is no longer taking in nutrients, and so that means that from that point on, the carbon-14 is starting to decay. It's no longer replenishing itself and actually keeping up with the carbon-14. So it's the rate in which that carbon-14 changes into carbon-12. So it loses electron over a certain period of time and turns it into carbon-12. All right. Ugh. All right, so solve differential equation involving inhibited growth and decay. So what did I say about inhibited?
It's something.
It's going to stop, right? Yes? It's not journey. Because with journey, they don't stop. Believe it. All right. Okay, so here is the whole model to go along with this. Where k is greater than 0, inhibited growth, right? Inhibited growth. Where m is also greater than 0, and m, did it state m here? No, it didn't state m here, but m should be my, no, I'm trying to remember. M is actually the what's it called? It's if you're growing and growing and growing to a certain point, that is the no. In an ecosystem.
Oh, that's the. Hold on. My tongue.
It's the amount that the ecosystem will actually maintain.
Carrying capacity.
Carrying capacity. There we go. Dang it. All right. Carrying capacity. I know it's in one of the other slides, and so M is going to be my carrying capacity.
I know it's so big.
Good job. So M is going to be the carrying capacity. So I'm going to have some capacity in which that there's going to be inhibited. So it cannot go beyond that. It cannot. It cannot exceed that. So so m is going to be greater than 0, a constant since k is greater than 0, and y is less than m. The derivative of this is going to be greater than 0, and y of t is increasing. Also, y is less than m because that's less than the carrying capacity. Guarantees the amount of y never be greater than m. So since the double derivative, so y double prime of t is less than 0, the graph of y equals y of t will be concave down. All right, now throw up those gang signs. Let me see concave down. Concave down, right? Concave down. So concave down. So this is the shape of the graph, right? So it's going to be concave down. So it's not going to go up. It's got to go down. So up to some asymptote, which is going to be the carrying capacity for that. So that is inhibited growth and inhibited decay. Okay, is it possible to have a decay less than 0?
I don't think so.
Okay, what's the capacity of that? Okay, how many people can you put on a plane? Think of the type of numbers.
157.
Depending on the plane.
Oh, okay, so now, real numbers, right? Okay, so now, do you know that 0.5 is a real number?
Positive numbers.
Okay, all positive numbers.
Whole
Okay,
numbers.
whole numbers. Whole numbers, right? Whole numbers. Whole numbers start at what? 0 and go up, right?
Yeah.
So even though a person's a person, no matter how small, okay?
Thanks.
So think of the number of people on the plane. So depending on how big the plane is, that's my carrying capacity. What is the floor of this argument? What's the lowest possible? 0, right? That's what we're talking about for the decay. It's going to go down to 0, and that's going to be it. Can't go lower than 0.
Bet.
I know. When I grade your test, then yes, I will agree that it can be lower than 0.
Cut the plane in half so that's like -1. Never mind.
A person's a person, no matter how small. Okay. Inhibited growth decay. M is the horizontal asymptote, which is my carrying capacity here. Here it goes.
And it's
Goes to that value. Okay. A lot of times when you actually have a decay, you're also going to have to some capacity on the bottom. So one that's actually used quite often in the argument of this is the population of rabbits. So let's say coyotes or wolves are the predator in that, they're the apex predator in that area. So that means they're the predator that kills and eats all those fluffy bunnies, okay?
yeah.
Those wascally wabbits. All right. If all those wolves die, there's not going to be anything keeping their population numbers in check, right? Okay, but let's say for instance, I have a lot of them die, okay, and so the rabbits increase. The rabbit numbers increase because the wolves have died off. So there's a lot more rabbits. But then the couple wolves that are still there, they have a lot of food available, right? So if they have a lot of food available, that means that they're going to procreate more, and their populations are going to go up. So when their populations go up, the rabbit population goes down. So it is a rotating cycle with the population of the wolves and the population of those rabbits in that ecosystem. So there is a carrying capacity on both ends, so that the wolves population could only go down to a certain amount, and the rabbit population also could only go to a certain amount. Yes? Okay. Newton's law of cooling. I don't think we do that one. Nope, we don't do Newton's law of cooling.
That look complicated.
Yeah, it is. I just don't do it. Okay. All right. Don't forget, like, share, and subscribe.